Hi everybody, this is the Advanced Algebra Trig Pre-Calculus video on section 1.5. We're going to focus on relations and inverses today. I know parametric relations are also in this section, but we are not going to be doing parametric relations. We are just going to look at relations, functions, and inverses, okay? And it's implied whenever you're talking about relations and inverses that you're going to talk about a function. Now, first, what a relation is. Okay, a relation is going to be any pairing of two variables. So this is any pairing of two variables. That pairing should be, it could be a list of points. They could be in a graphical form. Just in a graph. We could also show them in a table, all the different pairings that we have. But that's what a relation is. I think in the past what I've used is a relation of like age and shoe size. So your X would be your age and your Y would be your shoe size. And we would make just a list of those, and that would be my relation. Now, if a relation is a function, okay, so a function, you guys have had this before. A function is any relation where every x is paired with just y, with just one y. That y should also be predictable, all right? So a function is any relation where an x is paired with exactly one y. Okay, so for example, if I'm going to look at group A and then group B here, all right, let's say that this is the relation. Let's go with -2, 3, -1, 3, 0, 5, 1, 6, and to -4. Versus in B, let's go with -2, 3, -2, 4, 8, 7, -6, 2, and that'll be it. All right, so both of these are relations because they're just ordered pairs. I just gave you guys random ordered pairs, and one of them is a function and one's not, okay? Well, if I look at this guy, -2 is just paired with 3. -1, that's only paired with 3. 0, that's only paired with 5. And 1, that's only paired with 6. 2, so this is a function. Whereas here, -2 is paired with 3 and 4. This is not a function. All right, so let's just look at another situation. Let's look at situation C and D, and we'll look at these graphically. All right, and I will do my graphs in green. Hopefully you guys can actually see the green. Okay, versus. All right, so I'm giving you a parabola and a circle. Which one is a function and which one is not? Well, this guy is a function because for every x, there's just one y, right? Well, this one is not a function because like this x here, it's paired with two different y's. Therefore, that's not a function. Now, graphically, we can see if it's a function or not a function by looking at the vertical line test. If a vertical line just passes through one part of that graph, it is a function. If it passes through two, it's not a function, and it only has to happen once. So the vertical line test, this is going to state if the graph for a relation passes through vertical lines at just one point, like this guy right here, then the relation is a function. All right, then the relation is a function. Okay, So I could look at relations graphically. I could look at them in the table as well. That would be very, very similar to what I have in the points. All right, next one. Okay, so the next thing we're going to look at is what we call an inverse. An inverse relation, let's start with that. Okay, in order to have an inverse relation, you have to have a relation. You have to have some kind of set of ordered pairs. An inverse relation is taking the relations pairs and reversing them, flipping the x's and the y's. So, an inverse relation, the inverse of a relation is the set of ordered pairs where the relations pairs x and y have been flipped, or switched, I should say. Have been switched. All right, so we would flip those around. Okay, so for example, if I had the relation, let's say 0, 1, 1, 2, 2, 3, and we'll just go 3, 4. This is my relation. My inverse would be 1, 0, 2, 1, 3, 2, and 4, 3. All right, that would be it. Okay, so that's what an inverse relation is, and we're going to look a little bit more deeply at that in just a bit. Okay, now an inverse can be a function if each x relates to just one y. So, here's the thing. I'm going to look at that parabola again. All right? Would it make sense? Okay, so if I have a parabola, let's say I have a parabola like this. All right? And the parabola, that would be all of the x's and y's. So, for instance, you guys, I'm going to make this green. A parabola has points at -3, 9, -2, 4, -1, 0, -1, 1, my bad. 0, 0, 1, 1, 2, 4, and 3, 9. Because all I'm doing is I'm taking y equals x squared and I'm squaring my x's, and that's how I'm getting that. Now, the inverse for this, all you're going to do, and I'm going to do this in blue, we're going to switch the x's and the y's. So this would be 9, -3, and this would be 4, -2, and this would be 1, -1, 0, 0, still there. 1, 1 is still there, 4, 2, and then 9, 3. So we would still have points at 0, 0. Let's say this is 1, 1. And then we'd have a point, let's say at 4, 2. That would be like this. 9, 3 would be like that. 1, -1 would be maybe here. 4, -2. I'll make these better later too, guys. And this would be, okay. And that's not the best graph in the world, but that's my inverse. All right. So then the question is, okay, if this is, the original one is a function, okay, because every x goes to 1y, how can I see if the inverse is a function, meaning that every x here goes to 1y? So let's think about this. This inverse in blue, it's not a function, because from here we go at 2 of them. That's not a function. So it's not a function. So the question is, if I just look at the parabola, how could I figure out that it's not a function? Well, would it make sense that here are my vertical line test, that's where my x is, okay, where my x's are, that would be the same as my y's, that'd be my horizontal line. So we're going to say that the test for an inverse is a function if each x goes to every y, or the function, and that's the original one, that would be the parabola, passes the horizontal line test. Okay, it passes the horizontal line test. So it passes the vertical line test, then the function itself is a function, or the relation is a function. If it passes the horizontal line test, which this one does not, nor would the circle but there, then the inverse is a function. In this case, it's not. All right. Now, if a function, and we'll get to one, if a function passes the horizontal and vertical line test, then the function and its inverse are functions. That's weird. All right, if it passes both of them and the function and its inverse are functions, we call that 1, 2, 1. So if a function is 1 to 1, that means it is a function itself, which it should be, and then the inverse is also a function. All right. So I want to do a couple things with inverses because you guys are relatively new to the inverse world. And it looks like I have one of those too. So I'm going to start by looking at actually finding some inverses and then seeing if the inverses are functions or not. So I think I just saw one in here that I think I kind of like. Okay, so I'm going to go through here. And here's my first question. Okay, so I don't think I've done any examples. We've just had, and we'll call this example 1. And that's it. So we're on to number 2. Here we go. And I got to give you one more thing for notation. F of x equals the square root of x plus 4 minus 5, a function. Okay, the next question is going to be, is its inverse a function? If so, find it. All right. So first thing I would do would be to get my wonderful calculator out here, go to y equals, clear all this stuff out, and take the square root of x plus 4 minus 5. All right, zoom 6. All right, so that's what that looks like, you guys. Okay, so I'm going to get actually a piece of graph paper out, and I'm going to graph this here. And this will be my number 2. So the way that I usually graph things, this will be number 2. This is f of x, because it is a function, because it passes the vertical line test, just looking at it. This is going to be f of x equals, what, the square root of x plus 4, and then minus 5. All you need to do is go to the table, and there's an error at -5, which makes sense, because -5 plus 4 is -1, and you can't take a square root. So point at -4, -5, and we'll get better at graphing these in just a moment, too. Another one at -3, -4. Another one at, nice one, at 0, -3. Just take the nice ones. Another nice one at 5, -2. Do I have another nice one before I get to 10? No. So, looking at my graph, this is what it looks like, you guys. Okay, and then we'll look at some other things. So, that is a function because it passes the vertical line test. So, that is a function. Then, the next thing is, does it pass the horizontal line test? Yes, that means that its inverse is also a function. So, is it a function? F of x is a function. Since it passes the vertical line test. All right. Now, the inverse of it, okay, so I'm going to call that the inverse of the f function. That has a, it's like a f with a -1 in front of it, okay? That would be defining your inverse function. So if you go back into your notes on what an inverse function is, I'm going to put in here, if f of x is the function, f -1 of x, that means the inverse function. So this is your function notation, and this is the inverse. All right? Okay. Because everybody's going to have a pair. Okay, so my inverse is also a function. And I'll show that with the vertical line test too. But it's also a function because f of x passes the horizontal line test. Okay. So I'm going to do a couple things to find the inverse function as far as an equation goes, and then the table goes. So if I'm looking at f of x, you guys, here are my points. I have one at -4, -5. I'm only doing the nice ones. -3, -4. 0, -3. And 5, -2. All right, those are them. Okay, the inverse function, okay, we're going to take those x's and y's and we're going to flip them, okay, because in the points we'd flip them, so we're going to do the same thing here. Sorry if that wasn't straight. So we're going to go -5, -4, -4, -3, -3, 0, and -2, 5. Knowing full well that this was my starting point, so that also has to be my starting point, and I'm going to use green. So -5, -4 would be right here. -5, -4 would be right there. -4, -3, -3, 0. Okay, and -2, 5. So this was my starting point. So, all right. Good. Okay, so that's my table. Okay. Now, one thing is that if you're looking at the graph for a function and its inverse, okay, so this is the inverse, it's in green, and the function is in blue. A function and its inverse, they should be symmetric about the line y equals x, which makes sense because if I'm flipping the x's and the y's, it should be symmetric about y equals x. So a function and its inverse are symmetric about y equals x, that line. All right, so if I go in here and I draw this in here in red, y equals x would start at 0, and it would go up 1 over 1 or down 1 over 1. And let's get a there it is. If I took this and I folded it over the red line, which I could, and if we were in class, I totally would do this. I feel like that's actually pretty good. It is symmetric over that line. All right, so that's one of the relationships there. Okay, now if I want to find the equation for the inverse, all right, just like I switched the x and y around in the table, I'm going to switch the x and y around. And then you're going to solve for y. All right, so here we go. I'm going to change this f of x to a y because that makes sense. And I have the square root of x plus 4, and that's going to be minus 5. All right, guys, I'm going to flip those around and make it x equals the square root of y plus 4 minus 5. All right, I'm going to add 5. X plus 5 equals the square root of y plus 4. I'm going to square both sides. I'm going to have x plus 5 squared equals, taking the square root of, or squaring that, it's going to be y plus 4, and then I'm going to subtract 4. X plus 5 squared minus 4 equals y. That is my equation for my inverse. All right, and it should look like that. Here we go. So there it is. And then the other one is going to be y equals the quantity x plus 5 squared minus 4. And hopefully you guys there, hopefully you can see that. We'll do a zoom 6. I should be able to see the graph because I can see it over there. That is my function. Ooh, that's my inverse. Here's the thing, guys. Functions and their inverses should totally look the same. Same shape. These do. Why don't those? Well, when we get to graphical transformations, you're going to notice that, yeah, parabolas are the quantity x plus 5 squared minus 4. That is a parabola. That is a parabola. I only want half of the parabola. I only want the right half of the parabola. So the question is, how do I get just the right half of the parabola? So let's think about this. If I'm looking at the original one, this guy right here, and that would be this graph right here, okay, the blue one, wouldn't my domain here for my function go from -4 to infinity? So it's going to be -4 to infinity. That's in brackets, and this is in parentheses. And my range would be from, what, -5 to infinity? Okay. Would it make sense that since we're switching x's and y's to get the tables, we're switching x's and y's to get the equations, wouldn't the domain and the range, which is x's and y's, be switched? So the domain of the inverse is going to be the range for the function. And the range is going to be the domain. That should make sense. So here's the thing. I gave you a full parabola. I don't want the full parabola because that is what the equation is. I need to take only half of it. So what I'm going to do is I'm going to say, okay, I want my x's to go from -5 to infinity. All right? So we're going to say this is my inverse where x is greater than or equal to -5. Okay? Because you're going to have to change your domain. Okay? This means that there is an inherited restriction on the domain. It means that since the original one has a domain and a range that are restricted, particularly the range is restricted, that means the domain has to be restricted in your function. All right? So that's that. So here's another, before I get to maybe my last thing, I have to kind of look to see what I have. All right. When I'm looking at this, my function is an inverse if it passes the vertical line test. This did. Okay. Then to graph the inverse, all I did was I took the table of the function, flipped the x's and the y's, and that's my inverse, which is right here. To get the equation, I took the x's and the y's and I flipped them over there. All right. One thing I will add, when I took the equation here, what I should have defined this as not y equals, but the inverse of x equals. I should have used the inverse notation. Okay. So we have flip x's and y's in a table, flip x's and y's in the equation, and symmetric over y equals x. In this one, the green one was actually a parabola, so we had to restrict the x's to x's that are greater than or equal to -5, which is also the range over here. It had an inherited restriction on the domain. All right. Now, the other thing we could say about this guy is, you guys, these are 1-to-1. It is 1-to-1. And that's because it passes both the vertical and the horizontal line test. Sorry, I got kind of sloppy there. All right, so that is what an inverse is. All right, so we're going to look at one more, and then we're going to see, is it 1-to-1, yes or no, and why. And then we're going to implicitly look at, or graph algebraically decide if things are functions and inverses. And I'll actually do this one too. I'm going to hold on to that. All right, next one. Find the inverse algebraically. So this is going to be question, what, number 3? All right. So the function I want to look at will be y, or f of x equals x over x plus 1. All right. Okay, so that's what I'm going to end up looking at. Okay. So first thing I'm going to do is I'm going to change my f of x to y. And then what I'm going to do is I'm going to switch the x's and the y's. So this is going to be x equals y over y plus 1. And then we have to change this to x equals to get the inverse algebraically. I'm going to put the x over 1 and use cross products. I am a big fan of the cross products. 1 times y is y. That's going to equal x times y plus 1. I'm going to have y equals. I'm going to distribute this x through. We got xy plus x. Okay with that. All right, now I have too many y's. And what I can do is, wait a minute, I'm not. So I feel like I'm back where I started. I am, and I don't want to do that, so I'm just going to leave this alone. Sorry. All right, so 1 times y is y, and then I'm going to have x times y plus 1. All right, so next thing I have to do is I do have to get the y. Oh, I do have to get the y by itself. Sorry, I did like a brain block there. I don't like constipation because I just don't think that it makes sense. Like brain farts, just doesn't. It means to hold back. I am going to distribute this through. Next thing I'm going to do, I want the y's together. Let's subtract an xy. I know I'm moving an x, but that's okay. Y minus x, y equals, this is going to be an x. All right. All right, so here's the thing. I'm going to factor, I have too many y's here. Let's factor one out. All right, and last thing, get the 1 minus x out there. Let's divide by 1 minus x. So we're going to have y equals x over 1 minus x. So first thing I would do would be, okay, is this a function? It's the easiest way I'd look at it, okay? So I'm going to look at it this way, and then I can actually put my other in there. Original function is x divided by x plus 1. All right, and zoom 6. There we go. Yep, that looks like, that looks totally like it's a function, because if I draw a horizontal line or vertical line straight through, then if I go with a horizontal line, it looks like, yep, even though it looks like it's going to hit twice there, it totally doesn't. It's getting closer, like microscopically closer on each end to that line. So yeah, it is, the inverse is also a function. All right, so we would say, okay, this is my function. The inverse of that function is x over 1 minus x. And then I would also say that this is 1 to 1, meaning the function and its inverse are functions. All right, and if you wanted to graph the inverse, you guys, you totally could, but I think it's going to be a hot mess because it's going to be x divided by 1 minus x. See, there's my first one and there's my second one. It's kind of a hot mess, but if I drew a line down the middle, you can see that it is symmetric over y equals x. All right. All right. Now, this one also has a break in its domain, okay? So in this one, in the original function, I'll do this in blue. Your domain could be any number but -1. So we go, because the -1 makes it 0. So the domain is going to go from -infinity to -1 in union with -1 to infinity, okay? And then the range, my vertical or my horizontal asymptotes at y equals 1, because the degree of the numerator and the denominator are both 1. You take the leading coefficients and you divide them. So since, if I look at this, I'll get rid of this guy right here. Since there is a horizontal asymptote at 1, that means it's anything but 1. So it's going to go -infinity to 1 in union with 1 to infinity. Since x's and y's switch, you guys, domains and ranges are also going to switch, which makes sense here because the range is the domain of this. So the domain is actually -infinity to 1 in union with 1 to infinity. That's important because we don't really worry about restrictions on the range, just the domain. 1, your domain, your x can be anything but 1 because 1 makes the denominator 0. Okay? So if it's 1 to 1, we would say that the inverse of the function is x over 1 minus x. X cannot be 1. All right? Just like over here, x could not be -1. All right? All right. So that is all that stuff. All right? All right. I am going to go back to one of the other ones, but just to review, finding a function's inverse. Okay. By the equation, you're going to switch x and y, then solve for y. Okay. By the table, when you're graphing tables, switch x and y in both. I had an example of that before. Graphically, a function and its inverse should be symmetric over the line y equals x. All right. Graphically, when I find a function and its inverse, you guys, I always just take the table of the function and flip it for the inverse. That's all I do. All right, that brings me to the last thing of the day, and I may actually have to stop here because I think I'm going to run out of time. So I will make this a part 1, and we will have a part 2 shortly.